Hello everyone, welcome to the third event in our Be Curious series of lectures. It's great to see so many of you here. I know how busy everyone is. I'm just going to give everyone 20 seconds or so to sit down and get comfortable, and then we will start. So just bear with us. Right. I think there are quite a few people in now. So my name's Ritu Dand. I am the Chief Scientific Officer at Springer Nature, and I'm very excited to be hosting today's keynote speaker, Dr. Jane Rigby. We will shortly see some amazing images of our galaxies, planets, and stars, and I'm really looking forward to hearing and learning more about how they may have formed. I want to take this opportunity to thank Jane for making the time to join us. I know she's incredibly busy, so I feel we're very lucky. And I also want to thank you, all our editors, for joining us. It's great to have so many of you here with us today. So let me start by outlining what's about to happen over the next hour. The astronomers in the audience will know that there is a lively discussion on open data in this community. So I'd like to take this opportunity to give you a very brief overview of what's happening with respect to open data at Springer Nature. There have been some recent announcements that are of relevance to our editors. After that, Jane will give us an amazing talk, I'm sure, and that will be followed by a Q&A session, which will be moderated by Dr. May Chow, who is the Editor-in-Chief of Nature Astronomy. Before we actually get started, I do need to share a little bit of housekeeping with you all. So you can ask a question whether you are logged in or not by using the Q&A function to the right of your screens. You can type your question in at any point, and we'll take it at the end of the session. Of course, you're very welcome to also ask your question in person, should you want to use the old-fashioned way. You should also be aware that the session is being recorded. So many research communities, from computational scientists to genomicists, support open data policies. And as I mentioned earlier, there has been a lively and ongoing debate in the astronomy community about whether publicly funded telescopes, such as NASA's, should be allowed to have a proprietary period where images and spectra are archived and the data is not freely available for a year or 18 months until after the collection date. And this period allows the researchers who propose the initial observations to have time to analyze the data themselves and publish without being scooped. But the opponents of this so-called proprietary period note that this period also means that other astronomers are unable to use fresh data in their own observing plans. And so I was delighted to learn that the James Webb Space Telescope planners have already been progressive on providing immediate access to a key subset of data, namely the first 500 hours of observation, which were made during the first 5 months. And they cover all of Webb's key science areas, as well as their instruments. And this early release science program has allowed the entire community to learn quickly about Webb's instruments and capabilities, and perhaps most importantly, any scientific breakthroughs that come from this early data set would be discoverable almost immediately, which is great. And Springer Nature has been a great proponent of open science and open data. We know the importance that it has to accelerate discovery and make a greater impact on resolving our global societal challenges. And we have several initiatives in place to support our researchers. And I'll give you a very, very brief overview of some of the tools and the resources for both authors and editors. So we have a data help desk for use by any of our authors, where they can get customized support on how to make their own data sets open. We also have a data community where you will find resources and tools and the latest information on making data freely available and being able to use data in a fair manner. Several of our journals, as many of you will be aware, publish summaries and tutorials on how to use and interrogate data sets in a fair manner. And as publishers and editors, we all recognize that an open data policy helps to increase the integrity of the published paper by facilitating reviewer data checks, enhances the reproducibility of the research, and several studies have documented that making research openly accessible increases the impact of the published research. And in this slide, we recently announced a new policy that we are rolling out on all our journals, where every research paper will need to have a data availability statement, which clearly states how the data can be accessed, and for all original research articles. And we hope that this addresses the community need for measurable actions in the data policies area. So, right, I think that's enough about me talking about data, and I know you're all waiting to see the data. So without further ado, let me introduce today's keynote speaker, Dr. Jane Rigby. As many of you will know, Jane is an astrophysicist in the Observational Cosmology Lab at NASA's Goddard Space Flight Center in Maryland. And she serves as the project scientist for operations for the James Webb Space Telescope. In her work, studying how galaxies evolve over cosmic time, Jane has gained much user experience in active several telescopes. And she's also rightly been the recipient of numerous awards, including last year being featured as one of Nature's 10. And she's published more than 130 refereed scientific papers, although there may be some additions. I may have an older number here, Jane, and I'm very, very proud to be able to say that several in our own journals. The concept for the James Webb Space Telescope project was first conceived in 1989, and Jane has been a champion for decades. But she joined the team in 2010, initially working to restore capabilities that may have been lost due to budget cuts at that time. She's been one of the key scientists who have launched, deployed, and readied the James Webb Space Telescope for science. Please give a very warm welcome to Dr. Jane Rigby.
Right. Hello, everyone. Hello, local daytime to you, whatever that is. I'm in Baltimore right now, so it's 11 in the morning. I want to talk to you today about what we're learning from the Webb telescope. And I am going to start by pointing out that every image I'm going to show is real unless it has a big marker that says this is fake. That was a beautiful thing about getting a working telescope in space, is that I could throw out all of the artist simulations or conceptions. So this image is real. This is the selfie taken by the telescope of its own mirrors with one of our beautiful deep fields in the background. So I want to start by giving you the cartoon picture of how things are going. This is very not to scale. And I'm barely going to talk about 20 years of development, right? Just going to gloss right over it. As Rita said, this is a project that really got its start in the 90s and was the 2000 astronomy decadal surveys priority for astronomy, and finally got launched in December 2021. So I'm barely going to talk about the design, construction, integration, or test of this thing. Mention that it launched. I'm going to very briefly talk about commissioning, which was a 6-month-long process by which we deployed the telescope in space and then got it cooled down to the temperatures that it needed to operate at, and then got all of the 4 science instruments and all 17 science instrument modes working, as well as all of the onboard spacecraft systems. So that was a 6-month-long process that went from Christmas Day 2021 through to July of last year. And then, because I'm going to smoosh those parts together because I want to have more time to talk about science. We've had 11 months so far of science operations. We are finishing up our first year of science, and we've just selected our second year of science programs. We run in annual cycles or cadences of approved programs. And I should mention that all of our science is peer reviewed, is competitively selected. And so when I say we've selected our next year of science, that is selecting from 1,600 proposals received from researchers around the world with no restrictions on where people can apply from. You don't have to work at an institution that helped build the telescope, or even from a country that helped build the telescope. So we chose from among those 1,600 programs the top ranked 7th. So 6 out of 7 proposals are rejected, and then the top 7, the 1 in 7 fraction get approved for time on the telescope. So those observations will start at the end of this month, beginning of July. Okay, so let's launch right in. So that was the timeline. That was the when. I'm conscious that I'm talking to editors, so I'm trying to make sure I hit all of the who, what, when, where, why. This is the who. This is the Webb telescope, or JWST, as it's often acronymized. Here it is in a clean room in Los Angeles being prepared for launch. So that's back in December of 2020. And you can see that this is unlike any telescope that you may be used to, right? There's no dome, there's no long tube. This is a gold-coated telescope that is huge, right? You can see the size of the people and the cherry pickers there. That person on the right is at the same distance in the picture as the telescope. So you just get a sense of how massive this telescope is. A 6.6 meter diameter telescope, and then a sun shield that is the size of a tennis court. That's that shiny, the silvery thing below the gold mirrors, the gold-coated mirrors. They're beryllium coated in gold. That sun shield protects the telescope from the light of the sun and the earth and the moon. And I'll talk a little bit about why it has to do that. So this is this bizarre looking telescope because it has to do some very specific and difficult things. So the what that it needs to do is be an infrared optimized space telescope, and it was designed to be 100 times more powerful than its predecessors. That was basically the design requirement. And its science goal, JWST had 4 main science goals, but the one that was the elevator speech that sold the telescope, and that I'm going to spend most of the time sharing science results from, was about looking back to a time when the first galaxies were forming and understanding how it all got started, how galaxies got their start. So that was okay, we got the who and the what, now we got to do where. So this is a cartoon showing where this telescope is now. So it is 1 million miles away from the Earth at what's called the second Lagrange point, the L2 point. And so you can see that it circles the L2 point. So it follows the Earth around the sun in this orbit that never gets in the shadow of the Earth, and that is just going to keep doing that. We spend a little bit of gas every month or two to adjust the orbit to keep it in that orbit. So that's the where, 1 million miles from Earth. So this is very different, say, than the Hubble Space Telescope, which is only about 300 miles up, right? It's in low Earth orbit. This is a telescope launched 1.5 million kilometers away from the Earth to get it away from the hot Earth so that it can see deeply into space. Okay, so another animation, just to give you a sense of what this thing is. This is the telescope as it came off the rocket. And there are images of this coming off, but then the rest of this, we don't have images for because it drifted away from the rocket and we sent it toward the second Lagrange point and then it deployed in space. So the big technical hurdle for this telescope is that rockets are only so big, right? The rocket fairing for an Ariane 5, which is what we launched in, is 5.4 meters in diameter, right? So you have a 5.4 meter diameter fairing and you have a 6.6 meter telescope. So how do you do that? The answer is you fold it up. And so this is a telescope that was folded up tightly for launch and then deployed in space. And I'm going to show you the animation so you see that happens. In this animation, it all looks very automated and very robotic. In fact, we commanded every single thing that happens in this video, and actually like lots and lots and lots of intermediate steps. All of that was done by ground command and was done by people watching in real time, or a 1 second time delay, watching the telemetry as it happened to see, okay, did this do what we want? Did this do what we want? Okay, we're ready for the next step. So I'm going to show you the animation, but I want you to realize that this is 2 weeks of focused time watching every single step. So as we click through here, you can see the solar array come out. That's the only deployment we saw. The high gain antenna come out. These are the pallets that are going to hold the sun shield. The telescope rising up off the sun shield, the covers off the sun shield, that sun shield tensioning up with cables and pulleys and motors, the secondary mirror coming out, and then 6 of the 18 segments on those 2 wings coming out. So that all looks very smooth. What could possibly go wrong? This is the most complex deployment that NASA's ever done, right? This is a more complex deployment than, say, Mars Curiosity, which had the sky crane and landing a rover on Mars without crashing. The difference here is that we had more complex movements and actuators, but we were not under the time pressure, say, of the Mars mission. We could do this as, looking at telemetry at each step. Okay, so that's the deployed telescope. That's what it looks like in space. But of course, it's in the dark now with the sun shield. As you see these pictures, imagine that just remember that the sun is always in the bottom here, separating the telescope from the sun, from the hot sun, right? Okay, so let's go forward. So all of those deployments went flawlessly. And that really is a triumph of engineering. And so I'm going to present 3 different ways to think about this telescope, and then we're going to launch into the science. It is, again, a 6.6 meter telescope launched in a 5 meter fairing. And what this means is that we now know how to build telescopes that are bigger than their rockets. That had been a fundamental limitation. If you think about how big is Hubble, it is the size of a school bus because that's the biggest thing that could be crammed into the space shuttle. Right? All of our previous telescopes have been what we can fit into a rocket. And now we're not limited by that. We can build telescopes that fold up and then unfurl in space. That's an engineering triumph. It is also a telescope that deployed, and then it measures and corrects its own mirror, right? So the mirror, those 18 segments were at launch off with respect to each other by millimeters, and then driven interferometrically by ground command to an accuracy of tens of nanometers. So we can see exactly what's wrong with the mirror, and we correct it out by moving actuators. It's really beautiful. And that's a technology that really was built for this telescope, demonstrated, and is useful for a variety of other future telescopes. And then this is also a thermal engineering challenge, right? We've got one side, the hot side where the spacecraft is at 300 Kelvin, room temperature, nice and toasty. And then we've got the cold side with the telescope and the science instruments at 40 Kelvin, right? So think about the thermal difference between the hot and the cold side. And that's a huge challenge to keep those things separate. And then it's the sun shield that maintains that separation. It's passively cooled. There's no onboard cryogen, which means there's no time limit for how long we can stay cold. Okay, so that's the engineering. From a facility standpoint, Webb is the most powerful telescope we've ever built, right? Just in terms of how faint can we see, we observe for the same amount of time, about 3 hours, we, with Webb, can detect objects that are 100 times fainter than its predecessor telescopes, Hubble and Spitzer, could detect. So in astronomy, anytime we open up orders of magnitude improvement in capability, we discover stuff. It's an infrared optimized telescope, 0.7 to 28 micron wavelength coverage. That's the light that we see. 4 science instruments, and there are 17 science instrument modes that have a tremendous amount of capabilities, including coronagraphy, the ability to see a planet by blocking out the star, which is much more complicated than the thumb, but that's how I think about it. And then spectroscopy on each of those 4 science instruments, including slitless spectroscopy, multi-object spectroscopy, doing bunches of objects at once, and then integral field, where you get a spectrum for everything in the field. Okay, and then that third way to think about the telescope, it's really become, at least in the popular press, and I think to many of its fans, a symbol of cooperation. This is a telescope that was a collaboration among NASA, ESA, and CSA. So multiple space agencies, multiple nations. We estimate about 20,000 people worked on this telescope. So a huge undertaking of humanity. And we counted about 600 of us who commissioned it, got it working in space. And every year, about 2,000 scientists observe with the telescope, propose observations that are accepted. And then many more can get those data out of the archive through the sort of open data policies we were just talking about, or when the data go public if there is an exclusive access period. Okay, so that's 3 ways to think about it. These are just plots I made to show that, yes, indeed, that's your factor of 100 sensitivity gain. This is just how faint a thing can you see on the y-axis. The x-axis is the wavelength of the light. And you can see that huge gap in the middle there between what JWST can do in those bottom big solid dots and what the previous missions were able to do. And that's your factor of 2 orders of magnitude sensitivity gain. This is showing that gain. So that was for imaging. And that just shows what it looks like, right? The Spitzer IRAC image on the left, NASA's previous infrared telescope, and then the right, what we get from JWST. And the difference in depth and clarity is just it's eye-popping, right? We go much, much deeper. We also have a much bigger telescope, so we take much sharper images than the previous observatory Spitzer. This is that same plot as before, showing sensitivity, but this is for spectroscopy. I'm mostly showing this to convince you that I actually we did work on this. These are the measured and sensitivities from the results of commissioning. And again, what you're supposed to see here and say the middle of the plot is this 2 orders of magnitude, even more than 2 orders of magnitude difference between what we had before in the top with the dashed lines and what we have now with JWST, with NIRCam, NIRISS, NIRSpec, and MIRI, just showing the names of the 4 instruments in the solid lines, just more than a 2 orders of magnitude improvement in sensitivity. So great, what are we going to do with that sensitivity? Well, so the rest of the talk, I want to show you some science highlights, and I want to first say that it is to acknowledge the futility of what I'm about to do. I was asked to summarize all of the incredible science that we're doing and what it means, but don't talk too long. So that's a bit of a challenge. So what I'm going to do is pick and choose a couple things. There is so much science that I can't possibly capture. And in fact, I just got back from a science conference in Cambridge, Massachusetts, last week, which was just a week of geeking out about data from this telescope and what it's teaching us about galaxies and how galaxies are evolving with time, and in particular, how galaxies got their start. But I want to start this by first pointing out that we do soup to nuts. We study everything. I thought I would start with our own backyard. This is Jupiter from our own solar system. And one of those capabilities that Rita mentioned that I started working on when I got here was the ability to track moving targets. So being able to track objects that don't move like stars on the sky, fixed stars on the sky, but in fact are moving within our solar system, asteroids, planets. That was an ability that was lost for cost savings, and then we got it back because the entire planetary science community said, could we please use this telescope? And in fact, this telescope has such sharp imaging and such powerful spectroscopy that we are taking data on our own solar system that in many ways is like the data of missions that went there, right? So we're taking images of Uranus and Jupiter that look like they were taken from orbit of those planets rather than orbit around L2. So great, we can take very sharp images of the planets that are helping us understand our own solar system. But the reason I put this plot here is actually to remind you that the speed of light is really slow. And that's something that you need to know for the rest of this talk, okay? And what I mean is the speed of light is slow compared to the size of the universe and our ability to detect light, okay? So when we look at Jupiter, Jupiter is about roughly 5 AU away, 5 astronomical units away, 5 times more distant than the Earth is from the sun. And it takes light about 8 minutes to get from the sun to the Earth. All right, I can multiply 8 by 5. That's math even an astronomer can do. We get scared when math has too many numbers in it instead of X's and Y's. Okay, fine. Jupiter is 40 light minutes in the past. So when we see Jupiter, we're looking back in time by 40 minutes. Well, who cares, right? Jupiter looks the same now that it did 40 minutes ago. But now when we start thinking about galaxies and studying further, looking at things that are further away, that same principle is holding, right? When we're looking at distant stars, we're seeing them, they're light years away. We see them several years in the past. And now as we look into distant galaxies, that light that is arriving right now from each one of these galaxies has been traveling through space for billions of years, okay? So when you look at this image, this is the image that President Biden released in July last year. This was our first science image. But I want you to think about this as a snapshot of galaxies. Ignore the stars for a minute. The stars are from our own galaxy, but look at the galaxies in the background and think about it as each one is a little snapshot back in time, where the light is leaving that galaxy. It's been traveling through space for billions of years, and it finally gets to our telescope. And each of these galaxies that is at a different distance, so it's at a different look back time, okay? And you can very easily get into trouble because in its expanding universe, and it's actually tedious to keep track of the distances. The right thing to think about is the time. When I'm looking at any given thing in the distant universe, how far back in time am I looking? Okay, so this is what I mean by look back time. And as we zoom into this image, you can see there are hundreds of galaxies. The red ones are ones that have been gravitationally lensed. They've been distorted and warped. That's a thing that I study in my own research. And if you see the 2 galaxies that I have circled in yellow there, I'm going to pull each of those up in turn because we're looking successively further back in time. So that first one that we're going to pull up here at the bottom, which has been nicknamed the Sparkler for obvious reasons, that is a galaxy that we're seeing as it looked 4.6 billion years after the Big Bang. Okay, the universe is 13.7 to 13.8 billion years old. So we measure a redshift, and that's the thing that we measure. The measurable thing is the redshift. This is a redshift 1.38. That's how much the light has been shifted to the red by the expansion of the universe. And then we have a cosmological model that relates that redshift, what we measure, to what we actually care about, which is a look back time. So that galaxy we're seeing as it looked 4.6 billion years after the Big Bang. So about a third of the way back, or 2/3 of the way back, sorry. Now, what's cool here is if you see all those dots, this galaxy kind of looks like it has pimples, right? It's got dots all over it. Well, that's something that we think that these are star clusters, that this is a galaxy that is making that has both young star clusters and old star clusters. There's a series of papers there that I glossed that have analyzed the light from each one of those individual star clusters to estimate an age by how many old and young stars. Hot blue stars are young versus older stars. Once they've died, all you're left with is the cooler stars. And they've estimated ages for each of these star clusters, and they can tell us that some of these are like 1 billion years old. So this is a galaxy that is forming star clusters like our own globular clusters. We think this is how many of the stars within our own galaxy formed. Well, that's neat. Let's look at now at the other circled, yellow circled box. So that is a little red dot. It's a tiny little galaxy. And the spectrum of that, which we obtained in the first light images almost a year ago, the spectrum of that, I've highlighted the elements here that we see in the spectrum of this galaxy. This is a galaxy we're seeing only 600 million years after the Big Bang. So that light has been traveling through space for more than 13 billion years to get to us. This is the cool trick about using space telescopes, right? Or ground-based telescopes too, right? They really are time machines to show us what the universe was like in the past. And so when we look at this galaxy, we see not only we can tell how what its redshift is, so we can infer how far away it is, but we can see what the elements inside this galaxy. So we see lines of oxygen, hydrogen, neon. There are also lines of carbon and nitrogen that can be seen that tell us about how this galaxy is building up its chemical elements, is changing from the boring hydrogen and helium that was formed in the Big Bang to these heavy elements of oxygen, nitrogen, neon, carbon that are part of our world. And that in fact, certainly the carbon, nitrogen, and oxygen that we're made of that are ingredients for life. And so charting that nucleosynthetic buildup of the heavy elements is a passion of mine, and is one of the things that telescope does really well. Okay, this is just to say that there's a predictable relationship between these redshifts, the measurement on the y-axis, and the look back time, how far back into the past we're seeing for any given cosmological model. Okay, this is the furthest back that we have seen so far. I wouldn't be surprised if this chart is out of date, in a couple weeks. That little red dot on the right side there is a galaxy we are seeing as it looked 320 million years after the Big Bang. So we are seeing back 13.5 billion years into the past. And we know that because on the left side is the spectrum of that galaxy. The bottom is what it looks like in 2 dimensions, and the top is the collapsed 1D spectrum. And you see this ramp up and then a hard fall at the red line. And that's to the left of the red line, that's absorption by hydrogen in the universe between us and the galaxy. And it makes this very characteristic abrupt drop that you look at, and this will satisfy any astronomer to say, yep, we know how far away that galaxy is. That's the current record holder. And let's see a couple other examples too. So that's the furthest back we've ever seen. We really are finding galaxies that have already gotten their start. They've gotten going within the first 500 million years of the universe's history. All right, so here's another one that's even more impressive. This is a galaxy we're seeing as it looked 430 million years after the Big Bang. Again, you see in the left, there's no light. That's what got eaten by hydrogen between us and the galaxy, just in the universe. And then you see this very strong emission with lots of these strong emission lines from carbon, magnesium, oxygen, hydrogen, nitrogen. This tells us what is going on inside this galaxy. It tells us about how ionized it is. So the stars or even the black holes that are exciting all the gas, what kind of gas is inside of it. This is just a treasure trove for understanding what's going on in these early galaxies. This is just my favorite spectrum that we've obtained to date. And about 70% of all the telescope time is going to spectroscopy. So it's partly why I'm highlighting it hard, because that's the science that we're actually doing. And just for reference, so this is the spectrum that we took with JWST. I'm going to overplot here the spectrum that we had from Hubble, what we knew about this galaxy from Hubble. Hubble found this object. And there it is, right, to scale what we had from Hubble. And with Hubble, really, it was off to the left and on to the right. You could just see that, yep, okay, And if we just blink this a couple times, make that, that Hubble overlay disappear and then reappear, right, you can see the difference between what we could do with Hubble, which is maybe convince ourselves that, yes, it was very distant, and with JWST, where we can understand what's going on inside this galaxy, what it's made of, and how it's evolving with time. Okay, so I was trying to synthesize what we now know about early galaxies. And, you know, I will say it is very early days. And I get asked by reporters, well, how has this revolutionized? How has this changed our perspective? And I would say that, you know, my take on it is that we've basically found a new continent that nobody had ever been to or seen before, right? We have seen what the first billion years of the universe's history looks like. We are finding hundreds of galaxies at that epoch. And there's just a treasure trove of imaging and spectroscopy coming in. So it's all gorgeous. And I feel a little bit when I get asked, well, how has this revolutionized our picture? Like, look, we just found a new continent and you're asking how it's changed our knowledge of plate tectonics. I don't know yet. We're still figuring out, but this much is really clear. There are more high redshift galaxies than we expected. So galaxies in the early universe than we expected, and they're a bit brighter than expected. That doesn't break cosmology. That doesn't overturn our theories of how dark matter works. But it is interesting. It makes them easier to study, and it means that the universe got its act together earlier than we had expected. Galaxies get together, they build black holes, they get organized, they build their bars a bit earlier than we had given them credit for. These galaxies are brighter than we expected. And why are they brighter? Rachel Somerville at that recent conference helped me understand this really clearly. It's got to be one of two things. Either the stars are brighter, perhaps because they don't have as much of the heavy elements, so that they're hotter, they're not cooling as well, or they're better at making stars. Basically, that the process of converting gas into stars is much more efficient than it is in the local universe. So these galaxies have more stars. We're working out which of those it is. That's what the spectroscopy will tell us. There's a lot of work going on right now to find out how these early galaxies are different from galaxies in the local universe, to find out how they're influencing their surroundings and how they drove the process of reionizing the universe. So if we go to the next slide here, this is not real, and we're going to start this up. This is a simulation, a computer simulation of what that process might have looked like. So imagine we've got a universe that's full of dark voids. And then what you're seeing is the ionizing photons that are made by stars as the first stars form, evolve, shine out in the ultraviolet, and then blow up. And so you see these processes of both forming stars and then exploding. That what happens is all of that successive star formation is ionizing the neutral gas between the galaxies. And that process is called reionization. It has to happen so that we can see the universe. And it's the last phase transition of the universe. The universe is now ionized. It used to be neutral after the Big Bang cooled. And this is this process that we're seeing happening. And these early galaxies live in that epoch where the universe is going from completely neutral to completely ionized. Okay. That is my very extragalactic, I study galaxies take on some of our big discoveries. But I want to just highlight the work that this telescope is also doing to study solar systems in formation and to study planetary systems. So this is a result that I'm such a fan of from a recent, in the mid-infrared, of the star Fomalhaut. So an incredibly bright star with an Arabic name. And you can see the star is missing. It's been removed by one of these fancy chronographs, right? A very a complicated optical thumb. And so by removing the starlight, we can see what's beneath it, the light of a complicated planetary system where we have what looks like a Kuiper belt, right? This ring that looks like how our own solar system makes comets. There are gaps between these rings, and then there's an inner disk and an inner belt. And so we're seeing what looks a lot like an expanded, blown up version of our own solar system with an asteroid belt and Kuiper belt. So that's, we're seeing these planetary systems, and then possibly, it's thought that the way you clear out these rings is to have planets, which are shepherding the rings and then clearing out the debris in between. Okay, And that's just to compare to what we had before. So the green is showing what we could see with, at the same wavelength with Spitzer. And then, of course, if we go back for a sec, this is what we have now with JWST at the same wavelength. Okay, so we're going to go forward 2 here. Okay, we also are studying how, studying the atmospheres of planets orbiting other stars. So at the left is just an illustration of how that works, where we have a planet that goes in front of its parent star. When we use those carefully selected planets, we can measure the light that goes through the atmospheres of those planets. So take the spectrum now, where the planet's in front of the star, and subtract it from now, and the planet's not in front of the star. That difference is the light of the star going through the atmosphere of the planet. So you're getting to see the atmospheres of the planets of these stars. And so on the right is a spectrum, the transit depth of that of one of these planets. And all of these features we're seeing here are molecular features. And I've put the color coding from this recent paper proposing a fit to this system. And I don't really want to get into the details other than to say that it's clear that there are signatures of water, of carbon dioxide, of sulfur dioxide, of methane, of multiple elements, multiple molecules that we want to study to understand the chemistry of planets orbiting other stars. So that's certainly a huge focus for this telescope as well. So I want to close, and I'm happy to take questions by just saying that, clearly, the process of commissioning, which I glossed over in order to get to the science, but commissioning showed that JWST is the most powerful telescope ever built. We exceeded our design requirements almost across the board. It is 100 times more powerful than its predecessors. It takes sharper images. It is an incredible machine. And it is proving to be even more powerful than we expected, and we had very high expectations. It is also a very human endeavor. It is the product of tens of thousands of people around the world who built this telescope, and about 600 of us who commissioned it. And I am very mindful of that every time I use it, every time I get to work with data from it, that people around the world poured their hearts and minds and years into this mission. And space telescopes like this are not just a scientific facility, they're also really something to be proud of as humans, something that we've built, that the legacy of which will last. And so we are most of the way through our first year of science. We're anticipating a long mission with this telescope, and the discoveries have been rolling in to Nature and many other journals. And really, from my perspective, the best discoveries are still ahead of us. So thank you for listening.
Thank you so much, Jane. That was incredible. You not only managed to condense 3 decades, but 13 billion years into 30 minutes or less. So incredible. Obviously, the JWST is an incredible instrument, and it's not only the science, but it's doing so much amazing work in terms of scientific outreach and inspiring the next generation of scientists and engineers. I'm sure I'm not alone in having loads of questions. So let's just proceed with the Q&A. Do we have the first question ready? Okay, so why do telescopes take so long to build? 20 years is a long time. Does the technology not become outdated by the time it's launched?
That's a great question. And in fact, many of us have worked to figure out why it does take so long and how we could streamline those processes for building the next telescope, which I'm happy to talk about, the Habitable Worlds Observatory. Because there are places where we look at it like, we could make this go faster. This doesn't need to stretch out so long. I would say that JWST was a $10 billion investment from NASA, plus additional funds from the Canadian and European space agencies. It was a technically very difficult thing to build. And there were numerous engineering challenges that I can talk about. Part of the challenge is that these things are all one of a kind. And some of that is irreducible, right? We don't build 5 of these in a row, because if we did, by the time we got to the 4th one, we would be on a roll, right? Every time we're building something we've never built before. But some of these are things where, we could have spent more time working on it before we started really building it. We could have spent more time to better understand the technologies involved, so that when we went into production mode, it would have been faster. So in terms of the technologies being outdated, that's interesting, because from a space engineering standpoint, the opposite of outdated is heritage, right? We want things that we trust. So yeah, the onboard recorder for JWST is not a very big flash drive, right? We fill it about, I wish it were a little bigger. We can fill it with science data in a little bit more than a day. So we have to, twice a day, we have to empty the data off. But it's space hardened. It's trusted. We've used it on many missions. We trust it. It can get hit by tons of space radiation and it keeps working, right? So there are technologies like that where, yeah, it's not the cutting edge computers on board, but we trust them. For the science instruments, absolutely. Right now, we could build with bigger detectors. We could build more sensitive instruments in some ways. But yes, the process of building these things, the science instruments were delivered in 2014. We could build, if we were starting now, we could take advantage of advances in technology. But as far as outdated, no, not at all, because there's nothing better than it in space. So JWST was designed to do very unique things that only it can do. And so almost none of the science case was eclipsed by other missions because nothing else can touch it.
Yes, that's right. And let's not forget how far away it is. So it's not like you can go out and service it.
Mm-hmm.
It's not like you can go out and do any servicing at, L2.
Exactly. Not yet. Yes.
Okay, so the next question then, if one of the mirror segments is damaged, can you decommission that segment and keep using the remaining mirror segments? What would need to be done in order to do that?
Sure, let me get a prop. All right, so, show and tell time. So we have 18 primary mirror segments, right? And each one of them is individually addressable. We can move it in and out, up, down, tip it, twist it. We can even change the radius of curvature, right? So each of these is addressable. We do get hits from micrometeoroids. This thing is in space, and there are small pieces of sand in our solar system that occasionally hit it. We haven't had any hits that would cause us to stop using a mirror. But yes, it is possible to take, say, if we had one mirror that was very bad, that we didn't want to use anymore, we could basically drive it out of focus with respect. So move it in or out of this plane here, drive it very out of focus. And basically it would contribute a halo, a little fuzzy halo around all the images, but it wouldn't, we can do that if we want. We haven't needed to, and in fact, we want to use all 18 mirrors because that gives us more collecting area. But that is a thing we could do if we wanted to.
That's very good to know. Right, so the next question then, what is the expected useful life of the JWST?
Sure, so that's a great question, and the honest answer is we don't know. We built it with a 5-year minimum mission that we needed to get at least 5 years to accomplish the core science that we built it for. We also built it with at least 10 years of gas supply on board. So when we filled the propellant tanks, we put 10 years of propellant in. That is with some conservative engineering assumptions. And in fact, we got a fantastic launch, a fantastic mid-course correction. And we now think that we have fuel on board for more than 20 years of life. So before we launched, we were limited by fuel. And now we don't actually know what the limit is. We don't know if it will be fuel or if it will be gradual degradation of the sun shield and the telescope from micrometeoroids, but that's gradual degradation, right? The images just slowly get a little fuzzier. Or if it will be loss of capability to the science instruments, right? The science instruments are running at 40 Kelvin. They have a lot of moving parts. Eventually, they might wear out, but we don't see signs of that yet in general. And if that happens, we have 4 science instruments and 17 science instrument modes. So it would be loss of one capability probably, or slow degradation. And then we also have on board the spacecraft, right? The recorder, the computer, the radio that sends the data home. We right now have all the redundancy in those systems that we had at launch. So it's a long-winded way of saying that nobody knows. We will have to see. And as a scientist, I am certainly hoping and expecting that we have a long and productive science lifetime with this telescope.
That's great. Yeah, 25 years or more. Okay, so are there any valuable synergies between JWST and the Hubble Space Telescope? Or are we happy to just decommission the Hubble now that JWST is up and running?
Sure. So Hubble, there is some overlap in wavelength between Hubble and JWST, but mostly they don't overlap, which was on purpose. JWST was built to do the things that Hubble couldn't do, right? So it was very much built to be what Hubble can't do. And so in the region of overlap, so the sort of red part of the spectrum, 1 to 1.5 microns, yes, JWST is more powerful. It's a bigger telescope and it takes sharper images. So in that regime, when I get a choice as a PI, I'm proposing to use JWST for that part. And then JWST goes much redder than Hubble because, of course, it's a cold telescope. Hubble is a room temperature telescope. It's not sensitive in the infrared, in the thermal infrared. But what Hubble can do that JWST can't do is go bluer, right? We have gold, JWST has gold mirrors, so it can't go in the blue. Gold reflects blue light. That's why it looks gold to us, right? And so Hubble can do this color, right? And then bluer, which JWST totally can't do. And JWST and Hubble can go into the ultraviolet, which again is a wavelength of light that Webb cannot do. So for studying the massive stars, that are powering galaxies, that's a Hubble project, unless it gets so redshifted that it redshifts into the JWST bandpass. So there are terrific synergies between Hubble, which is seeing the blue light, and JWST, which is seeing the red and infrared light, that we want to keep Hubble going as long as it's still scientifically productive.
Yes, thank you for that. The next question, how will data from JWST be shared with the scientific community and the public?
Sure. So JWST is not a survey observatory. It's not like the upcoming telescope Roman, which is doing a series of surveys throughout the sky. The way that Hubble works and that JWST works is carrying out about 300 science experiments every year from that were competitively awarded, that were proposed by teams. So that means we could be looking at an asteroid before lunch, and then we do a deep field, and then we're on to Jupiter, and then we go out and do an exoplanet atmosphere. Like, we're doing this lots of different science. Most programs have so all the data go public, and they are shared at the MAST archive. You can download them. Any person in the world can click through and download the public data from JWST. Large programs go public immediately. And as Rita alluded, the early release science programs have all their data public immediately. And I'm the principal investigator of one of those programs. All our data are public as soon as we see them. In fact, I've seen some of our data on Reddit before I had a chance to download them. Most data have a 1-year exclusive access period, which is the word I like more than proprietary, because proprietary means something else. But it's secret for a year to the teams that proposed it. That is currently NASA policy. As Rita alluded, there's a lot of change in opinion right now about how that should be. But we are planning for this year and next year to continue with that small and medium programs have that 1-year secret period so the team can figure out how to make the data behave. There's still a lot of instrumental issues to take out. You want to make sure that when you're publishing a result, you're actually telling it's a result of the universe and not of the detector or the science instrument that you're misunderstanding as an astrophysical signature. And so that's the plan. But then all of the data go public in the archive and are available for investigations by anyone around the world. And in fact, I think that half of all the papers coming out of the Hubble Space Telescope at this point are using archival data rather than new observations. So there's a lot of reuse of this data. It gets used by multiple teams, including the team that proposed the data. And then with the public, I mean, there's a whole there's the whole NASA press release machine in which we are. There is a whole process of sorting through submitted papers to find the ones that are worth promoting and sharing with NASA press releases and image releases and all of that. But ultimately, papers are written and those data are out there. The results are available to the world.
Right. So, well, in the same vein then, can you discuss the role of machine learning and artificial intelligence in analyzing JWST data?
So that's an interesting question. And honestly, the role right now is that there is not a lot of either machine learning or artificial intelligence being used to analyze JWST data. I will say that the JWST data that I'm analyzing, I am old school. I mean, we're talking like Lorentz and Laplace, and Gauss, right? I mean, we're fitting Gaussians of our emission lines. We fit polynomials. It's very, very old school in a lot of ways. That's in part because the data that we're taking, in terms of any one investigation, often is very classical in how we want to analyze it. I think the role for machine learning and AI comes when we start pouring through the archive and we start doing meta-analyses of all the data that's been taken or a subset of all the data that's been taken. And so I think, for example, combing through all the data and finding rare objects that might have been missed, that are where you need to go through all the data we've ever taken, looking for some rare objects like weird kinds of quasars or very obscure galaxies, for example. And that's where we may want to give it some training samples of, okay, here's what you're looking for, now go. That sort of work it's coming, but I think we're going to see more of it as we start building up a bigger and bigger archive, and there's a richer data set to go mine for that kind of work.
Yes, no, that's, yeah, sorry, I'm just blown over. I mean, it's just so incredible that you're already talking about, years past when you then, look back, the reams of data that have been generated.
Well, we have the advantage of our big brother or sister Hubble, right? Hubble's now more than 30 years old, and we can look back to that telescope and see how the archive has built up and how meta-analyses are possible. And so we can look to our teenage years, right, by looking ahead to Hubble's history.
Yes, exactly. Well, we're nearly running out of time, and I'm going to try and squeeze in another question.
Go for it.
What contingencies are in place in the event that JWST experiences technical difficulties or malfunctions in orbit?
Sure. So I'm talking to you right now from Baltimore at the Mission Operations Center for JWST. And just down the hall from me is the Mission Ops Center, where we talk to the telescope twice a day. We download our data once a week. We give it our instructions for what it's supposed to do next week. And in this building, folks plan the observations for the next week and do all of the work of keeping the telescope working and at peak efficiency. Like any space mission, occasionally we have hiccups. I will say that to date, and I should find some wood to knock on, We've had fewer than I would have expected. We had a smoother commissioning period than I think we had any right to expect. But in commissioning and normal operations, occasionally we get hiccups. And what happens, there's onboard software that first of all is designed to keep the telescope safe. No matter what, keep the telescope safe. If there's something happens, the telescope gets data that doesn't make sense to it. I know I'm making it sound sentient and it's not, but if it gets data that's not supposed to happen, especially anything that indicates that an uncertainty in where we're pointed, right? Because we have to always keep the sun shield in between the sun and the telescope. If there's any possible confusion about that, the telescope safes itself. It has sun sensors, so it knows where the sun is, and it puts itself in a safe attitude and then radios home for help. That's the short answer, is that there's this, and there's a whole series of beautiful fault management, and this is where there are fault management engineers that have worked out in great gory detail different contingencies and what the telescope should do in response, that is all designed to make sure that we keep the things safe. If a science instrument gets unhappy, again, I know I'm making it sound sentient, but if it gets telemetry that doesn't make sense with internal consistency checks, then that same thing. The observatory safes that science instrument, says that a science instrument is no longer available for science because it's given some weird results. And then it phones home and says, hello, this science instrument is not behaving. And here's the data that is confused, that seems concerning. And then we go look at it. So the contingencies really is, and then, all of our cell phones get a text message and we all WebEx in whatever time of night it is. And we go look at the data and figure out what's happening. And first of all, make sure the observatory is safe, which it should be doing by itself. But we also want to make sure that we're telling it to do safe things. And then we figure out what happened. And it's a very human process where we get the right experts in the room, in the WebEx, and we look at the data, we understand what happened. And it's often things like, oh, that's a weird edge case that can happen. Or, oh, we got hit by a cosmic ray, which can happen, right? You're in deep space, you get hit by a cosmic ray, and a computer says, oh, I didn't know what that was. What was that? Well, okay. And then we have a whole recovery procedure. So the real answer is there are gobs and binders of contingency plans for exactly this sort of thing, and onboard fault management to keep the telescope safe, and then radio home for instructions, and then a team of engineers and scientists, mostly engineers and technicians in this building, that work through what happened and how do we fix it to get it back up and running and doing science again.
Amazing. Well, that's very reassuring. We've gone past 5 o'clock, so I'm wondering, probably Ritu will now want to sum up.
Thank you, Jane. That was absolutely fascinating, amazing. I'm not a sci-fi person, but this was real life, and it was absolutely fantastic to hear you talk about it all. I am supposed to just come on and say thank you, everyone. It's time to go, but it's also my prerogative to be able to ask you one last final question.
Go for it, Ritu. Go.
You may humor me for a minute. I'm itching to know, have you come across any intelligent signs of life? And I'm thinking water, not aliens. Have you come across any such data, and how conclusive is it at this point?
Sure. So everybody wants to know, can we find another Earth? And the short answer, which I'm just going to tell you right now, is we're not going to do that with this telescope because it wasn't designed to do that, and it's too red. What JWST can do is look in the habitable zone, right? The Goldilocks zone where there might be liquid water, and see whether planets look like they could maybe be habitable, right? Which would mean liquid water and nice, nice cozy temperatures. That's great. It would be nice to know if there are planets that do that, that look cozy. What you would not want to do is book a trip yet, right? This is not a telescope that you should use to book your interstellar space plans. And the reason for that is that we can't look at Earth-like planets around sun-like stars. We just can't. The physics is wrong. There is a plan and work to build such a telescope that would use much of the same technology. It's called Habitable Worlds Observatory. It was the top recommendation from the last National Academy's decadal survey, Astro 2020. And that's a telescope that would look a lot like JWST. It would be segmented, but it would be in the blue or UV. And that's what you need to do sun-like planets, to do Earth-like planets around sun-like stars. So if we want to find actual evidence for life, things like chlorophyll, things like carbon dioxide out of equilibrium, right? All the chemistry of life on Earth that we can see if we look back at the Earth from space, you would need to build a telescope that is not JWST. So just to set expectations, that's not JWST. It wasn't built to do that. It's too red, it can't do it. But we can use the same technology, right? The wavefront sensing, the multiple telescope, the multiple mirrors, the deployment in space. So all the same technology, we could build such a telescope. We just need the go-ahead.
Thank you. Well, I won't wait for it then from this study group. Okay, I really do have to say goodbye and thank you now. Thank you to all our editors for joining us today, and a big thank you to Jane for making the time to take us through this amazing project and what we've learned to date. Thank you again.
Thank you for joining us. Thank you, Ritu and May.